Let us consider the third example on solving the second order homogeneous linear difference equation with the constant coefficients. The question here is to solve the difference equation yk plus 2 plus 2yk plus 1 plus 4yk equal to 0. Of course, it is a second order difference equation which is homogeneous because the right hand side is 0 and it is with constant coefficients and it is linear. Now the first step is to write the given difference equation in the form where we find the shift operator. So how to write that? We have to take the shift operator on yk. So if we take the shift operator e twice, that is e square on yk, we will get yk plus 2. Therefore this yk plus 2 has been written as e square of yk plus 2 as it is. Yk plus 1 can be written as e of yk, because when we operate e on yk, the answer will be yk plus 1. Therefore this yk plus 1 can be written as e of yk plus the last term is 4yk. Let us keep 4 within the bracket and yk outside the bracket, and on RHS it is 0. So after having this form, now we can write the auxiliary equation. Auxiliary equation is r square, that is we have to replace e by r in this bracket. So it is r square plus 2r plus 4 equals to 0. It is a quadratic equation, algebraic equation with the variable r. Now this equation is to be solved. In order to solve this equation, we prefer either a factorization method or the formula method. But in this case, we find that the factorization is not possible. Therefore, we will prefer to use the formula method. So therefore, it implies r equals to minus b plus or minus square root of b square minus 4ac divided by 2a. That formula we are going to use. So here minus b is minus 2 plus or minus square root of b square, that is 2 square is 4 minus 4 into a is 1, c is 4. 4 into 4 it is 16 divided by 2a. a is 1, it is 2 into 1 is 2. So therefore by using the formula we get r equal to this much. Now we have to simplify this radical. We observe that it is root of minus 12. Root of minus 12 can be written as root of minus of 4 into 3. So root of 4 can be written as 2 outside the square root, and this root of minus 1 is that is imaginary unit, and it is root 3 remaining within the radical. So therefore the value of this root minus 12 is 2i root 3. So using that value over here, I can write r equal to minus 2 plus or minus 2i into root 3 divided by 2. Now we can separately divide and we can have r equals to minus 2 by 2, that is minus 1, plus or minus 2 by 2, that is 1 into I into root 3. So the roots we obtained in this case are the pair of complex roots. So what type of roots we got in this case? A pair of complex roots we got. So when we get the pair of complex roots, then what is the procedure of writing the general solution of the given difference equation? That is yk equals to r to the power k into the bracket c1 into cos of k theta plus c2 into sine of k theta. Now here we have to tell what is the value of r and what is the value of theta. So the value of r is square root of alpha square plus beta square. So what is alpha? Alpha is minus 1, beta is root 3. So it is square root of alpha square minus 1 whole square is 1 plus 3 square is root 3 square is 3. It is already root 3. If you take square on that, square and square root cancels, it is 3. So 1 plus 3 is root 4. Now root 4 is 2. So the value of capital R we got it as 2, and the value of theta is tan inverse of beta by alpha. So it is equal to tan inverse of beta. Beta here is root 3 by minus 1. Alpha is minus 1. So it is tan inverse of minus of root 3. We know one important thing here, that tan inverse of minus x is pi minus tan inverse of x. So therefore it implies theta equals to pi minus tan inverse of x here is root 3. So we have used one of the important trigonometric formula, that is tan inverse of minus x is pi minus tan inverse of x. Therefore the value of theta we found here is pi minus tan inverse of root 3. So we know that tan inverse of root 3 is pi by 3, that is 60 degree. Therefore it is pi minus pi by 3. After taking LCM and simplification, it is 3 pi minus pi, it is 2 pi by 3. So this is the value of theta we have obtained here. Substituting this value of theta, that is 2 pi by 3, and the value of r here in equation number 1. Equation number 1 implies yk, that is the required solution, yk equals to 2 to the power k into the bracket c1 into cos of k into 2 pi by 3, that is 2k pi by 3, 2k pi by 3 plus c2 into sine of 2k pi by 3 in the same way. So this is the required solution of the given difference equation. Let us consider the fourth example. Find the particular solution of the given difference equation given that y0 equal to 1 and y1 equal to 6. When we compare this problem with the previous examples, we come to know here that we have to do some extra work in this case. Here we are given with two conditions. We have to use those two conditions and we have to find out the particular solution. What is the particular solution? We will be getting the general solution after solving the auxiliary equation, and in that general solution there will be the arbitrary constants present, that is C1 and C2. The arbitrary constants will be present in the general solution. By using these conditions we can evaluate the arbitrary constants and substitute in the general solution to get the required particular solution. So that job we have to perform in this particular example. So let us start the solution. So from the given difference equation we come to know here that the difference equation is of the form e square minus 4e plus 4 operated on yk equals to 0. By the definition of shift operator, e square yk is yk plus 2, eyk is yk plus 1. Therefore this difference equation can be put in this format. After writing like this, we can write the auxiliary equation by simply replacing e with r. It is r square minus 4r plus 4 equals to 0. Now we have to solve this equation. So in order to solve this equation, it is very easy to factorize. So the factors are minus 2r minus 2r, because minus 2 becomes minus 4, minus 2 into minus 2 becomes plus 4. So therefore the factorization is a simple task here. Now we can take r common between first and second terms, so as to have r minus 2 within the bracket, and here minus 2 can be taken outside. Then we will be having r here. Here it is plus, therefore we should write minus because minus sign has been taken outside. Now here we should write 2 because 2 has already been written outside. So within the bracket it is r minus 2 and RHS is 0. Now r minus 2 is common in both of the two terms. Therefore if we take r minus 2 common here, here it remains r for the first term, minus 2 for the second term. So here it is r minus 2 into r minus 2. So therefore, by equating this bracket equal to 0, we get r equal to 2. By equating this second bracket equal to 0, we again get r equal to 2. So what type of roots we are having? We are having the real roots but identical roots. The roots are real and identical. When the roots are real and identical, we know yk. How to write yk? The general solution yk can be written as c1 plus, what is the variable here? It is k. Independent variable is k. K into c2 into whatever root we get, that root to the power k. So it is 2 to the power k. So this is the general solution of the given difference equation. Call it as equation number 1. Now we have to do some extra job in this problem. That is, we need to find the particular solution from this general solution. So in order to find the particular solution from the general solution, we will be using these two prescribed conditions. So let us use the first condition. Given that y naught equals to 1. What is the meaning of this? When k is equal to 0, y is equal to 1. We should understand here, that is at k equal to 0, y is equal to 1. The meaning of this is this thing. So let us substitute this into equation number 1. When we use this condition in equation number 1, that is in the general solution, y naught is 1, so it is 1 here on LHS, and on RHS wherever k is there we are supposed to put 0. So it is equal to, on RHS it is bracket c1 plus 0 into anything is 0 into 2 to the power 0 is of course 1. So this gives us c1 equals to 1. So from this it is very easy to know that the value of c1 is 1. So after having the value of c1 equal to 1, we can get the value of c2 by using the second prescribed condition, that is y1 equal to 6. Also, it is given that y1 equal to 6. What is the meaning of that? That is, at k equals to 1, y value is 6. So if we use that, equation number 1 implies we have to use this condition in equation number 1, that is the general solution of the given difference equation. So if we use that here, it is 6 on LHS because y1 is 6, and wherever k is there on RHS we have to put 1. So it is c1 plus 1 into c2 into 2 to the power 1. So if we simplify this by taking 2 to this side, 6 divided by 2 is 3. This implies 3 equals to c1 plus c2. But we know that the value of c1 is 1. Therefore, if we substitute 1 here, it is 3 equals to 1. This implies 3 equals to 1 plus c2, or by taking 1 to this side, it is c2 value we are getting here, 3 minus 1, that is 2. So we got the value of c1 and c2. Therefore the general solution 1 now takes the form of the particular solution. The general solution 1 now becomes the particular solution because we are assigning the particular values to the arbitrary constants present in the general solution. So the value of c1 is 1. Let us write on LHS it is yk, that is equal to c1 is 1 plus c2 is 2. 2k, let us write it as c2 is 2, k is present there. So c1 plus k, c2 we have written into 2 to the power k as it is. So what we have done here, we have obtained the values of c1 and c2 by making use of the prescribed conditions, and in this way we got the particular solution of the given difference equation. So this is the required solution, and this completes the solution of the given problem.